So for the third talk, so I'd like to discuss some work of these authors, Claudio Carlos, who is in Mexico City, John Fay, who is a postdoc at Arizona, but he has a position at Soochow, and so this work is we're going to try to derive SPDE as a hydrodynamic limit, and so one can think of it in two ways. One can think of the SPDE itself. So there's some constants. So one can think of an equation, an SPDE like this, where this is a spatial white noise, and phi and psi are some smooth functions with some nice properties. Okay, so so this equation, you know, so in d dimensions, this is in minus d over 2, you know, just a minus epsilon. So this is the regularity of this. And so the gradient will be in, you know, just one less. And if the functions are reasonable, then the parabolicity of the equation should indicate that rho is you get 2 more plus 2. So so this is only positive in dimension 1. So in dimension 2, it just barely fails. Okay, so so rho, you know, should be a function, and you know, it's a distribution otherwise. So so this of course, you know, this is a, you know, it's not, you know, just there was a talk earlier last week. You know, you're multiplying a distribution times a function. So this is a singular SPDE. You have to define it carefully. Okay, and so that comes to the other part, other motivation of the talk. We're going to try to derive something like this as a hydrodynamic limit, and even if you look at it as an SPDE, how do you make sense of it? I mean, the talk last week, and you know, the theme in SPDE is to regularize the noise. You convolute it with a kernel or something like this, and then this is well defined, and then you know, then rho will depend on epsilon, and so then you let epsilon go to 0, and hopefully you get the you get something which is corresponding to the equation that we wrote down. Okay, so the in terms of hydrodynamics, we're going to try to derive this equation, where this will come as a scaling of a certain random environment. Okay, so that's the theme of the talk. Okay. So, okay, so so the random environment, you could put what we were interested in is this so-called Sinai random environment, and I'm going to describe that in just a few minutes. And so it will turn out that this random environment is strong enough to survive in the scaling of hydrodynamic limit. It will give rise to some term like this, and you know, at the end I'll mention tag particle in the system as well. Okay, so hydrodynamic in random environment is a well-studied subject. Okay, so if the so just to mention some previous papers. So if the environment is ergodic enough, it's allowing enough movement, then it will emerge in the hydrodynamic equation, but usually as some sort of homogenized deterministic quantity. And so there are lots of works on this, and as I just put one which is fairly recent. Okay, so one can go back into the literature from that paper, for instance. But there are only a few works where the random environment survives in the scaling so that the homogenized object is actually random itself. And so I just mentioned, so and these are usually, these have been with exclusion or independent particle systems. So so this first paper is with respect to exclusion. So it's the probabilities of movement are given by conductances on bonds, and the conductances are random and may not allow as much movement as some other bonds. And so the particles are trapped in some way, and so for instance one emerges with this hydrodynamic equation, and this W is the contribution from the random environment. It'll be a realization of it'll be an alpha stable subordinator. Okay. So okay, so let's come back to our problem, and so we're going to be looking at a zero range particle system. Independent particles is a case of it. Okay, and so you have some here. We're going to stick to dimension 1 for the reasons mentioned, and so we have some particles here. Agreed. And so let's look at the random environment. So consider Wn. This will be the polygonal path of fair random walk. Okay, so the increments of this are IID random variables, mean 0. Okay, and so the idea is that if a particle is here, it's going up, so it tends to move more to the right than at this location when it would move to the left because of the slope. Okay, so the increment here is positive, whereas the increment here is negative. So this is the reason. So if you put the particles in this environment, so you can see that you may have some trapping. It may be difficult to you want to move somewhere, but then you're pushed back and things like this. Okay, so let's be more precise. So let's look at a Sinai random environment, which is one of the classic random environments. So let UX be let's say IID random variables, and let's impose that the expectation of the log of this fraction is 0. So in this case, the random walk will be recurrent. Okay, and so here's an example, and so if you now consider one random walk in this random environment, then so given these r's, for instance, in this particular example, then you move to the right or to the left with these probabilities. Okay, so it's almost symmetric, but well, in this case, it depends on the sign of Rx, how you go. Okay, all right. So the classic result is that so you can imagine from the previous previous slide, this is the cartoon, and so there's some. The random walk is here, it tries to move this way, but then it wants to come back this way, and so it's not moving much. And so the scaling, Sinai showed that the scaling is log n squared. It's logarithmic scale. So, and with this scaling, one gets one gets a limit, which was clarified more in these papers. Okay. And so because you're scaling by log stuff, there's no functional central limit theorem associated with this. You'll just get it's a trivial one. Okay, so but one might like to know what a continuum version of Sinai random walk is. So Brock's, so this is also classical. So Brock's wrote down formally this diffusion. Okay, and of course it's not well defined because W prime is not well defined as a function, right? So you can think that this is the continuum analog of the discrete random walk in random environment, and in fact, okay, so this is the informal. Okay, what's going on? Yeah, sorry. Okay, so this is the informal description. The formal one is you can do it in terms of a speed scale, and then you do a time change, and so this is a more careful description of the diffusion, and so Brock's showed that you go in the same sort of log t squared scaling to the same limit. Okay, so this is his result. Okay, so and both results, by the way, are in the averaged or annealed sense. Okay, so so to connect the two, Seigneurel considered scaled random environments. So the Sinai one was just 1/2 plus or minus Rx. So we're going to divide Rx by square root of n. Okay, and so so in this case now Rx is just IID mean 0 with some variance, and so you have the same sort of setup. Let's now scale the edge size by 1/n, and so now you can try to formulate a limit theorem, and he showed that. In diffusive scale, that you will converge to, so it's a functional central limit theorem to the Brock's diffusion. Okay, so this is his result. Okay, so we're going to try to use those random environments. So let's come back to the particle system. Zero range, we've mentioned this before, but let me just go through it again very briefly. So at a location, there's a clock. It rings with rate number of the particles, some function of the number of particles. Let's call it g. And once the clock rings, then at random one of these particles jumps probability pxy. So in this case, it'll be pxy is not translation invariant. It'll depend on the location x. Okay, so so this is informally the process. You can write down the generator. So this is exactly what we have here. So eta xy is just the configuration which is updated by moving a particle from x to y. Okay, and this is the rate of that happening. Okay, so in the case g of k is equal to k, this system is just corresponding to independent random walks. Okay, and so we'll be working also on the torus, so not on z. Okay, so with this setup, so we're going to take now the zero-range jump probabilities as let's just do a first try. So let's take it according to the Seigneurel environments, the sort of Sinai type environments. Okay, so from x you go to plus 1 or minus 1 with this probability if you've been selected. Okay, so we have the environmental, the empirical measure in diffusive scale. Okay, so it's almost a half, right? This is very small. So so things seem to be almost on the symmetric scale. So diffusive scaling seems to be reasonable, and so we have the formalism of hydrodynamics. I have this cartoon here. Maybe we can just go quickly past this. So this quantity is just the average number of particles in this interval, scaled interval, and this should converge to some mass on the macroscopic interval. Okay, so in this business, we just apply the Ito formula to this evolution of the average particle numbers, this quantity here, and so we should compute the drift term. Okay, so this so you get this computation here. I guess we could do it. Is it clear? I'm not sure. People have done this before, I guess. Yeah. So I mean, we could just do one step. So this is. Okay. So here's the generator, right? So the generator is here. Okay, so you're going to you have a possible transition from x to a neighbor. Okay, and so the particle number at so from x to x plus 1, the particle number at x will go down 1, and the particle number at x plus 1 will go up 1 in this business, right? And so let's write this out. So this is what is this? This is L applied to 1 over n, sum over x, g of x over n, eta n squared t of x. Okay, so when we do this transition, we could do z here. So when we do this transition, this will decrease 1, and this will and the one next to it will increase 1, and so when you're applying L, this is your function that you're applying L to, and so you have a difference of, so this is what we're calling f. And so you have this difference, and so things cancel. So this will be present in after you do it, but you'll have a -1 and +1, and so you could rewrite this as 1 over n. Okay, we're going to speed up time, right? It's n squared, right? Because that's corresponding to the diffusive scale, and so then we have sum over the possible transitions. So this possible transition is, so at x plus 1, you increase by 1, so you have this one term, okay, but you decreased at x. Okay, and then that's multiplied by the rate of this transition. So this is going at rate that's going at that rate, and so that's g of eta of x. And for us, remember this px x plus 1 is 1/2 plus rx over square root of n. Okay, and you could also do the plus minus business. So you'll have something like this and like this, and so this is the generator that you get. The 1/2, you can do, if you add that over, then you'll get this discrete Laplacian of g. Okay, and so that's this term here. Okay, I guess there's a 2, right, from the jump rate. Okay, and then you have this term here, this little weakly asymmetric term. Okay, and so that one, let's look at that. Okay, so that one is giving us. So let's do the +1 first, right? So what do we get here? We get. So we get n squared over n, right, times 1 over square root of n from this rx over square root of n term, right? And then we have a sum over x. Okay, we have this this difference. Okay, and then we have this rate, g of eta of x. Okay, and then we have times rx. Okay, so this is what we get with the plus term. With the minus term, you'll have g of x minus 1 minus g of x, but just take the take minus of the difference, so it's g of x minus g of x minus 1. We're on the torus, so bring it back. And so there's a minus sign here, but there's also a minus sign here, and so you just add. And so that's why you get this 2. And so you'll get this. You'll get this expression here. So now one of these. So anyways, let's go ahead and cancel some things. So this is just n. So this n. So we have this. So let's go ahead and. Okay. So let's go ahead and put square root of n here. As in the slide. And then we have to multiply here by square root of n. Okay, so what do we get here? So we get so we should get what we get here. So let's see. So this is oh yeah, I have to divide. Sorry, not I multiplied here by square root of n, so I have to divide. Okay, and so this gives you the right stuff, I think. So this is so this n will go on to this difference, and so this is just equal to. Let me copy the first term. So this is already normalized. So this is of order 1, right? And then we have this extra term here. So this is 1 over n. Agreed? So there's a 2 over n here, sum over x. And then I'm calling this as this gradient. And then it's all multiplied times this this term. Okay, so this is how it's going. Okay, so maybe it's many of you have already done this calculation before, so sorry if I'm saying something that you know. Okay, so this is the origin of this term. Okay, and so let's go further. Okay, so intuitively, so if we think of this is microscopic x. So in terms of macroscopic space coordinate, let's call it little a, we can think of x as n times little a. So if x is equal to this this value, then we think of r as the increment of the polygonal path. Okay, and so we have that here, and so square root of n. Let me rewrite it as n divided by square root of n, and so this so this is almost if you think of this as Brownian motion, then if you think of this as the difference of Brownian motion at 2 very close points, then you're getting, you seem to be getting the derivative, the white noise that we wanted. Okay, but of course you can't do any of this. Okay, but if you could, and if the G homogenized, and the quadratic variation, in the hydrodynamic scale, will go away. Okay, so it'll be 1 over n. And so with some convergence, one may be able to get to this equation. Okay, but it's ill posed. Okay, and this intuition we're doing, we can't actually do this. So we can't do this as in terms of a function. Okay, so the idea is, as we mentioned in the beginning, is we'll try to derive something with a regularized noise and then take the limit. Okay, so how to derive something with a regularized noise? So we have to change the environment a little bit. So let's smooth out our environment. So this was the environment that we started from, the Senurel ones. So let's just consider QX instead of RX. QX would be an average in a small macroscopic window. Okay, and let's take this var epsilon positive. Okay, and if this is one way of doing it. Another way would be to convolute with a different. Here you have the average. Okay, but you could also average with respect to a different kernel. Okay, so you go through exactly the same calculation that we just did on the board, and so we would get this term because we're using these environments, right? It's the same formalism. So we have now this this business. Okay, but remember now QX is a little bit nicer. So QX, let's go back to the average one. So QX, this is just the something to do with the polygonal process or the partial sum process of the increments are the mean zero increments. And so we know if we divide this by square root of n, then this should go to Brownian motion. So you have an extra 1 over square root of n here times 1 over square root of n times this. 1 over square root of n times this is approximately Brownian motion, and so that's so this intuition that we had before seems actually more reasonable now. So is that okay? So you see here that this is if you divide this by 1 over square root of n, then this is the this will converge to Brownian motion at n epsilon minus Brownian motion at epsilon minus Brownian motion at minus epsilon. So that's this is business here. Okay, so that is in some sense the main trick. Okay, so you have this extra 1 over 2 epsilon on the bottom, but remember epsilon is fixed throughout the talk, throughout this part of the talk. So so this is the main idea is that this QX is already has a built-in quantity which is converging to something reasonable as a function. Okay, so so this is the main idea. So so if you accept that, then and if we just call this as this, you can think of this as some sort of this difference quotient is close to what we might call the derivative, and in the other case you would get this as what that W prime epsilon is. Okay, so so you can see here the regularity of this is c to the 1/2 minus, and here it's it could be it could be a little bit more if psi is 0 at the endpoints. Then depending on the smoothness of psi prime, you can bump up the regularity of this. Okay, so that may be useful. Okay, so okay, so informally this is the result. Okay, so we're going to be able to converge to this equation, and so you see here, in contrast to the board, this function and this function are the same. That's because of the dynamics that we chose. Okay, and so we'll be doing both annealed as well as quenched. The annealed result would be that you would converge to this would converge to this object, the law of that object, where this is just this is a function of the Brownian motion. Is it okay with this QN business and everything? Okay, so maybe I could just say that we're in some sense we're slightly cheating. So we went from 1/2 plus or minus Rx over square root of n. This is Senurel. Okay, and we are now going to 1/2 plus or minus Qx over square root of n. Okay, and Qx is what's the order of QX? So QX is QX is this, and so this is approximately 1 over. So let me pull out this epsilon square root of n times 1 over square root of n times this sum. Okay, so this is approximately this x, x plus epsilon minus w of x minus epsilon. Okay, so this, you can think of this as the difference of Brownian motion on these 2 points, right? But you're picking up this extra factor, so that's qx, but we're dividing by an extra square root of n, and so this is roughly 1/2 plus or minus order 1 over n. Okay, and that makes a lot of help for us. So that's the trick. So okay, so this is the informally the result, and the zero range process more carefully. We would like to have some good mixing, and so there's some assumptions that we put in order to have some uniform mixing rates, and we're going to be working on the torus, and so what's the invariant measure for zero range under when the pxy, the jump probabilities, are inhomogeneous? They're still product measures with these marginals. This is the probability, the marginal probability of k particles is this of g of k factorial is just g of 1 times g of 2 up to g of k. Okay, and the phi depends on x, the phi that's in here, and so this is the link to the pxy or the random environment. Okay, so the phi x satisfy this equation. Okay, and so and the number c here is you can think of that as a density parameter, and so you can vary c. There is mass conservation in the system. Okay, so this function phi you can also think of as the expectation of g with respect to one of these marginals, and so subject to the mean number of particles being this value alpha. So it's in some sense a mean jump rate. Okay, initial conditions, we're going to just distribute them according to one of these local equilibrium measures, which means let's just say a product measure where the number of particles at each location corresponds to some macroscopic function. So the number of particles here would be with mean rho naught of x over n. Okay, so quenched formulation. So remember the q's are random. So here's the polygonal path corresponding to qx, and so we can find a probability space where this converges almost surely to Brownian motion. Okay, so we're going to be working in such a space. So and omega will be fixed in the quench setting as one of the realizations where this convergence happens. Okay, and so then more carefully the theorem, even this is slightly informal, but so we'll converge to this where rho is the unique weak solution of this in a certain class. I won't write down the class. Okay, so okay. The annealed one is, as we said, so you, with respect to the law of the random environment, the empirical measure will converge to this this random measure where the rho will depend on the law of omega prime epsilon. Okay, so so if you accept this first step, okay, then you know, then the interest is in taking epsilon to 0. So so this is in another work, and this will go in a para-controlled sense. So this rho epsilon will converge to this rho naught, which will be the solution of a fixed point problem, which is can be interpreted as this equation. Okay, you know, I won't go too much about that in this talk. Okay, so let's get to some open questions. Okay, so this is the point of this talk. So you know, we did this two-step procedure where we we derive something with regularized noise, but you know, I mean, in some sense, initially when we were thinking about this problem, we were actually only looking at the Sen-Urel environments. Okay, and so these are the unregularized environments, and can one start from that and then get the para-controlled solution of this? Okay, so that's an interesting question. And can we say something more about the statistics of this rho naught? It's random, right? So okay, so those are a couple of questions. So here's some partial work. So with respect to independent particles, so here, g of k is equal to k, and 5 rho is equal to phi. Just 5 rho is equal to rho, and in this case, the annealed mean of this random variable. This is basically, as we said, this is the average number of particles in some box. This will converge to this expectation, and xt is Brock's diffusion. Okay, so this is actually following from some, you know, in Claudio's book, he has a calculation for independent particle systems, where he captures the if you start from if you start from some Poisson product of Poissons, then at time t it will still be Poisson, but the means will change in a certain way according to the random walk scaling that's present in your model. Okay, so in our case, the Sen-Urel random walk scaling is going to Brock's, and so this came as a calculation from that technique. Okay, so tag particle. Okay, so in fact, Carlos, co-author of this paper, you know, he was interested in approximating Brock's diffusion from particle systems. In fact, so if we look at the tag particle, so xn t is the location of the tag particle at time t. So this is unscaled. T is unscaled. Okay, then this is the drift term. So you know, the particle here will jump right or left. It jumps. You know, the clock here has to ring. The clock here rings at a rate which is given by the number of particles on the location of your tag particle. That's what this notation in the numerator means. And then you have to, the tag particle has to be selected, right? So that's, so 1 over the number of particles is the selection probability of selecting the tag particle to move. Once you select it, it moves right or left with probability 1/2 plus or minus q over square root of n. The 1/2 terms cancel because the jump rate, the clock jump rate is the same going right or left. And so the only thing that survives is the asymmetry in the jumps, which is this 2q over square root of n. Okay, and there will be also a martingale term. Okay, so if you scale this diffusively, okay, then one can kind of guess what the answer is. So you know, remember q is has an extra square root of n in it, just as course, you know, just as we mentioned here. And so if you put in all the scalings, you know, you're speeding up time by n squared, okay, and then you're so this is in diffusive scale. Then you know, so this this particle number should approach the density value at the particle scaled particle position, and these this, as we did in the previous computation, should converge to this. Okay, so this is the drift that you get, and there will also be a martingale term which is now present in the answer, and it has this limiting quadratic variation. This is what we expect. Okay, and so you can see, so in other words, this VT satisfies this STE, should satisfy this STE. Okay, a lot of epsilons. Okay, and so if you take the example that you're in the linear case, independent particle system case, then you see that you know, this factor is just 1, and so you get back formally some approximation of Brag's diffusion. Okay, and actually one can take the limit of this and actually get Brag's diffusion in this particular case. That's not too hard. Okay, so the okay, so this limit is ongoing. A student at Arizona has more or less done it in particular cases. Let me just mention, you know, what are some of the difficulties. So, you know, you're approximating the particle number at the tag particle, the particle number here, by some macroscopic density. So you want to kind of approximate this by some local macroscopic density, and then take the width to 0. You need continuity of the solution to do that. Okay, and so that's going back to the PDE. So it's going back to the PDE here. So if this is smooth enough, then, you know, there's some classic results. So we're still investigating what happens. So in the case when this is just the difference of Brownian motion, this will be c to the c 1/2 minus. It's just you know, so there's some extra things that we have to do to ensure that rho is continuous. We don't need rho is continuous to prove hydrodynamics. Okay, so, you know, there's some things like that, and also the SDE is you know, it itself, you know, it will have pathwise uniqueness if things are regular enough, and it'll be only in law otherwise. So there's some, anyway, so this is what's going on. So And this is building on some work that Milton and Claudio and I did some time ago when there was no random environment. We were just looking at tagged particle in the zero-range system starting from a local equilibrium measure. Okay, and of course this is, you can, it'd be interesting to take the limit of this as epsilon goes to 0. Then of course these things, the para-controlled solution should emerge. Okay, so the main problem is that the environment is not spatially homogeneous. It's almost spatially homogeneous. Okay, but so the current way we're doing it is we're using the average in time to allow some mixing to help us to do the approximations, the replacements. And okay, so maybe I can stop at the moment here, and then we can discuss if there's any discussion.
Does it give you a regularization if you take Qx instead of an average, sort of some reversible Markovian environment where the probability that you have plus is the previous or the next is plus is still is almost 1 with that for n large. So like.
So instead of IAD, I.
Time to time you change a lot of minus, right? Which is a sort of regularization, but less.
Yes.
The probability of changing is of order 1 over epsilon n.
If that's the case, then that should be enough regularization to do it. I mean, this is you see, this type of asymmetry is very well suited for hydrodynamics in diffusive scale. So it's this is much stronger.
So I was thinking something like your order 1 over square root of n, but not all the time.
Yeah, it all comes down to this, this calculation that we did on the board here. So, so it all comes down to whether you can handle this term. So, if you have a pxy, so this will be maybe x to x plus 1, something like that, x plus or minus 1 r, x plus, if you want to bring that in as like a Markov chain or something like this. So
maybe I understand. So maybe that's what I was proposing is reasonable in their needed sense. That thing will be of order 1 over n. Yeah, okay. It was not.
One can introduce some space dependence. We didn't do that. At the moment, if I go back to what was here before, so Rx is IID, but you could make it non-identically independent, I think. The Markovian thing that you're mentioning might also work. To get a particle system where you have a different function, that could be interesting to look at. Not quite sure what particle system that would be, but that might be an interesting question. The direct limit, I think, is an interesting question, even for independent particles. So even if you're in the independent particle system setting, I think that's an interesting question. It's yeah. I mean, I'm not sure. This equation, it is a nice one. There's no renormalization needed in the limit epsilon to 0. Okay, so the windows you know, if you take a smaller window than you know, you'll still have to you know, deal with this. I mean, so if you have QX, so QX is of a smaller window. So so I think it's as you suggest. It depends on how you can understand this in the macroscopic scale. So yeah, so that's I don't have much more to say besides that. So it seems like by adding the random environment, we're able to get some noises, and so there may be some other ways, other environments which will give different noises or something like this. So this is what I'm suggesting. Yeah, I think you know, we'll have to so there will be some expansions. I mean, we'll have to maybe to reformulate this, the convergence of this as a fixed point problem. So we haven't we haven't gone too much into this yet. So I think there's definitely some questions to figure out.
Well, if not, let's thank Sunder for these 2 lectures.